I'm going to try to spend 20 minutes introducing instance-based analysis. Some of you who were at Steve Edwards' talk yesterday got a very brief overview of this. I'm going to tell you what instance-based analysis is in our online tool, Matilda. Arathi, actually nothing to do with the image behind me. That's a whole different talk on my maths and art project. We're not covering that today. Today we're talking about graphs, and we're talking about features of networks, features of graphs that are predictive of how algorithms perform for different things. I'll illustrate all of this with a case study from university timetabling algorithms, because some of you will know that university timetabling problem is underpinned by a graph structure. Mostly what I want to talk about today, though, is the role that graph features or network features the role they play in helping us to understand algorithm performance, whether that's on problems that are directly on graphs like traveling salesman or shortest path or graph coloring, but also some of the other problems that we apply algorithms to solve that have an embedded network structure that may not be explicit, but you can extract a network structure from it and measure interesting things. And then I'll discuss some open challenges at the end. I've just changed the slide. You probably can't see it yet, but I'm going to talk about the whole motivation for my research with instance-based analysis. It's all about how we can trust algorithms, why we need to trust them and how we can trust them. So we all know that algorithms guide machines to solve problems, and it doesn't matter whether it's for the big end of town, helping them make more money, or whether it's, you know, algorithms to help people do stock market trading, or algorithms for face recognition or other things. In the end, we develop algorithms that will support decision-making as long as we trust them. And of course, it's a very topical issue at the moment of how do we ensure trust of algorithms. And what it comes down to is how do we test an algorithm to establish trust under various conditions and all the conditions that will matter into the future. So the basic idea of how we might have an algorithm, how we test it, is to throw examples at it and throw examples where we know the behavior we want the algorithm to have. And if we test it rigorously enough, we might gain some trust. Of course, we could bury our head in the sand and we could just only test a limited number of examples to convince somebody, like an editor of a journal, for instance, that our algorithm is good by cherry picking the examples that will make it look good. But that's not what we're trying to do, right? We're trying to be honest and we're trying to genuinely establish the strengths and weaknesses of an algorithm. And you might have to search a little bit harder. You might have to come all the way down to example N before you start to see where the algorithm has a weakness and is failing. There might be another algorithm where you see immediately its weakness, but before we dismiss it, we have to recognize that all algorithms have strengths and weaknesses, and it's our responsibility as researchers to exhaustively search, and that's not practical, so we have to be smart about the way we search the space of all possible test instances to establish the conditions under which an algorithm can be trusted. So the choice of test examples is critical, and it should be unbiased, diverse. They should be challenging for the algorithms. Don't just throw easy examples at an algorithm and say, hey, I can trust it. They should be discriminating. The examples should help us see what one algorithm's strength is over another. And they should be include real world like examples so that we can understand whether there's going to be some deployment disaster in practice. It might be that the algorithm does well on synthetic contrived examples, but not so great on real world problems. We need to understand all of this. And unless we can guarantee that our test examples have these important properties, the results are going to be inconclusive at best and dangerous at worst if the algorithm is doing something quite important. So essentially what I'm trying to do with my research, and my laureate fellowship for the last 5 years has been developing this, is to attach a warning label to algorithms, in invisible, not explicitly, but attach a warning label to algorithms that basically says this algorithm should only be used for the scenarios most similar to those described in the terms and conditions which guarantee its reliability. So what are those terms and conditions that we have to understand? Well, it's really hard to establish the terms and conditions for algorithm trust with the standard approach to how we test algorithms, because in the darkness of these black boxes, not only is the algorithm often a black box to people, the developer may understand it, but if you're selling it, most people treat an algorithm like a black box they're trying to trust. We have a suite of test examples and we pass them through the algorithm and we have some kind of measure of whether we should trust it. Did it get it right? What was its accuracy or error? We've known for decades now that we test algorithms incorrectly. There's a lot that can be improved here. because the problem is most of the time this suite of test examples is also treated like a black box. We don't get in there and scrutinize the quality of those test instances. You tested your algorithm on 1,000 examples. That sounds like a big number. It must be good. Let's pay attention to this trust metric. On average, across the 1,000 examples, how did you perform? Oh, you got 89% accuracy. That sounds pretty good. Right? It's all not enough detail to give us trust. So the first problem is that scrutinizing a bunch of test examples to ensure they're trustworthy is actually a mathematical and statistical challenge. How are we going to see what those test examples are like? Rarely do I feel convinced that randomly generated examples are going to reveal anything useful. Historical data doesn't necessarily prepare us for uncertainty of the future. So just because you've taken some real world problems from the past and tested it doesn't tell us anything about how the changing conditions in the future may cause us to question the trust of the algorithm. And how do we know what examples need testing in theory and in practice? How can we be convinced that you chose 1,000 great examples as opposed to 1,000 useless ones? The second problem we have is this black box over here, that when we report performance on average across a bunch of test examples, that averages hide all sorts of sins, because just because an algorithm is good on average doesn't mean you should always use it. We're failing to recognize the weaknesses of the algorithm, the danger moments where we shouldn't be using that algorithm. So under what conditions can an algorithm be trusted? We need to understand, and when will it fail? Okay, so these are the problems with the standard approach. And what Matilda is trying to do, or my instance-based analysis methodology, and Matilda is the online tool, essentially it's trying to crack open this black box of test problems. You tested your algorithm on 1,000 problems. Let's see them. Let's not see them as a list of file names. Let's see them visually as points in a space, and we can see their diversity, and we can see their bias, and we can see the theoretical boundary of where you could have tested and whether or not you've really comprehensively filled that space. That's what Matilda's trying to do. And then within that, we can overlay algorithm performance, and we can say, well, how does this algorithm perform? Where is it good? Where is it bad? How does it compare to a competitor algorithm, for instance? And that's how we can visualize the trust of the algorithm. So Matilda is the online tool. As Steve briefly explained yesterday, it's an acronym. It's got lots of other nice connotations with the Australian soccer team, women's soccer team and other things, but let's not go there. It's all on the website. So the goals of instance-based analysis then, as a methodology I've been developing over the last 13 years. And it's aiming to understand and visualize the strengths and weaknesses of algorithms by cracking open a test suite for insights that would otherwise be hidden, and to inform us about which algorithm should be used when and why, under what conditions. What are those mathematical terms and conditions where you can trust it? We're trying to facilitate an objective assessment of algorithmic power across the whole space. Not my algorithm's really good because I tested it on these 10 problems, please publish my paper. How does your algorithm perform across the most comprehensive, the mathematically proven most comprehensive space? We're trying to improve research practice, the quality of papers submitted to journals and the evidence people present for their new algorithms' reliability. We're trying to establish algorithmic trust for the real world. And we're trying to avoid deployment disasters when an algorithm is used when it shouldn't have been used. And history is filled with many examples where algorithms have gone wrong. That's another talk I normally give, not the 20-minute version. And we're trying to guide the generation of new test instances, the most comprehensive suite of test problems for well-studied problems, and by trying to control the characteristics that those problems have. And in this way, we're expanding the existing benchmarks to make sure that they're fit for purpose. Many of the existing benchmarks that people apply their algorithms to are no more interesting than randomly generated problems. We have to be able to do better than that if we're going to get insights and drive algorithmic advances. So we have to know what is the quality of our testing benchmark suites at the moment, and how can we improve them. So there's many steps to the methodology. The core 5 steps I'll talk you through with a quick case study. But basically, before we apply the methodology, we collect data. This is a bunch of test problems or instances, features, measurable features of those. I'm going to come back to features in a minute, because many times we're using features of networks or graphs. And we have to run algorithms on those instances and collect performance metrics. Once we've got that metadata, we create the instance space, which involves some feature selection and dimensionality reduction to 2D. We can visualize the location of the instances in the space. We can visualize how algorithms perform. The footprints are the regions where an algorithm is demonstrably good. We can explain those strengths and weaknesses. We can do some automated algorithm selection using machine learning, and we can say, if your instance is like this, you should use this algorithm. And then after the analysis, we can get insights into choice of new features, where we might need new instances, where new algorithms need to be developed, and we can repeat, and it's an iterative process. Let me take you through an example of university timetabling, because it's something that we all understand well. Suppose there are two excellent algorithms. They were both winners in the international timetabling competition. And I'm trying to decide which one is best. Say I'm a university and I'm trying to purchase timetabling software. Which one will I buy? Well, I've got 8,199 test examples of university timetabling problems. So RMIT semester 1, that's one instance. RMIT semester 2, that's another instance. University of Melbourne semester 1, one instance, right? I have 8,199 examples where you would run a timetabling problem. Of those 8,199, 21 come from an Italian university. These are the competition instances that were used years ago. There are 4,492 randomly generated timetabling problems and 3,686 real-world-like instances. I won't go into the details, but it was a paper I published years ago where we took the random generator and we changed it so it would become more real-world-like, using the Italian university instances as the inspiration. So here's the instances, 8,199 broken down into the three types of instances. We have algorithm A, which is best 25% of the time. Algorithm B is best 29% of the time. And algorithm A and B give a tied performance 45% of the time. So which algorithm would you buy? If you were a university and you were charged with finding a suitable algorithm, you would probably say, oh, look, for most of the time, algorithm A and B are both pretty good. They're very competitive algorithms. They're both winners in the competition. They're both great. You're not buying a dud algorithm. But if you had to pick one, you go with algorithm B, right? Because it's got a slight edge. Black box here. Averages hide all sorts of sins. I'm going to show you why you should be concerned about a decision to use algorithm B. You don't know where your university timetabling problem is in those 8,199. You can't see that. Let me show you. So the question, which algorithm is more reliable? We need to crack open these 8,199, not just labeling them by where they came from, but let's label them by their characteristics, their features. What do the properties of the problem look like? I'm going to have to go faster than this. So basically, I'm going to step through the 5 steps, but in the end, I just want to show you the pictures. So which features should be selected that are going to explain performance, and which dimensionality reduction method should we use? Here's the answers. We had 32 features of timetabling problems. We selected 5. We defined good performance as the algorithm that has the smallest number of timetabling clashes for students. That's the objective to minimize. This is my 2D projection. It won't make any sense to you. What I want to show you is that I'm measuring a timetabling problem. I'm summarizing by 5 features. 2 of these features are to do with a network. Some of you may not know that a university timetabling problem can be represented as a graph where 2 nodes are connected. Nodes are events that have to be timetabled, and the 2 nodes are connected by an edge if there's some reason that those 2 classes cannot be scheduled at the same time. In other words, the same lecturer, for instance, or they both need the same room. Yeah, then you connect it with an edge. So there's an underlying graph coloring problem that underpins a solution to the timetabling problem, because you're trying to color those edges where the color represents the period. Enough said. Event degree teacher connectivity and event degree teacher mean weighted are both features that are measured from the underlying graph. The rest of them, number of one-room events, how many events that have to be timetabled can only be scheduled in one room. This is an important characteristic that makes the problem easy or hard. And slackness. Slackness is the ratio of the number of rooms you need to the number of rooms you have. How tightly constrained is the problem? So every timetabling problem is summarized by a 5-dimensional feature vector and projected into a 2D space by this optimized linear transformation. Don't worry about the details. It's all in this paper if you're interested, but we basically project to 2D so that I can visualize the instances. And here's the visualization. The red boundary is the mathematical boundary where all instances lie. An instance is a point in this 2D space. The blue ones are the 21 Italian university instances. Notice that they're all quite similar to each other from year to year. The timetabling problem doesn't really change very much in its characteristics. A few more students, an extra classroom, but it's pretty similar. The yellow ones are randomly generated problems, and the pink ones were our real world like random generator modified problems. You'll notice that these 8,199 problems, as much as that sounds like a huge number, they don't fill the space. There are other timetabling problems that could have been constructed over in the left, but we don't know how algorithms perform on those. But from this visualization, we can ask questions like, this suite of problems, let's crack it open and ask, is it diverse enough? Does it fill the space? Is it biased towards a particular region where maybe one algorithm has a particular strength, and maybe we're just throwing in examples at one algorithm who's going to solve it well, and we might get a biased perspective. Is it challenging enough? Is it discriminating? You can't necessarily see those in this 2D space, but we can see that through more analysis. And does it span a range of real world contexts for likely deployment? So if you were an Italian university, you'd want to know which algorithm is going to be best up in the top right. And it's not so relevant to you which algorithm is best somewhere else, right? So we need to be able to see all this. We can superimpose algorithm footprints, and we can ask which algorithm A or B is predicted to be good and where. Blue is good, orange is bad. We can see that the algorithm A, which was the simulated annealing one, is good at the top and bottom, but not so good in the middle. And the taboo search is good at the bottom, but not so good at the top. So remember, oh, I didn't tell you, algorithm B was taboo search. So algorithm B was better on average, but it has this clear weakness at the top. If your timetabling problem was at the top, you should use algorithm A, even though on average, algorithm B was slightly better. I'm going to skip all the details here, but this is the kind of analysis you can see in Matilda. You can get these visualizations of how different features, so these were graph features, how they vary across the space. And you can say, okay, what is it about the top that made algorithm B have a weakness? Oh, it has high values of this slack property. All right, so now I know if my problem has a high slackness, I shouldn't use algorithm B. You can explain these kinds of things. Okay, and then of course you can do support vector machine algorithm, pick a winner, which method should you use where? And so you end up saying use algorithm A at the top, algorithm B at the bottom. In this gray region, don't use either of them. Both of them are a bit unreliable or too close to call. Okay, so I'm going to skip all that detail and just get to the point about the importance of graph features. So in Matilda, we have lots of problems that we have solved using instance space analysis, us and people around the world, in collaboration with us and independently. And the ones that have an asterisk here are the ones that use graph features. So there are some problems here that are obviously on a network structure, like a traveling salesman or a graph coloring problem. There are others like timetabling where the graph is a hidden component of the problem, but you can extract a graph and you can measure some things that explain algorithm performance, as it turns out. So you can see all the ones that are, the ones in white are the ones that are currently up there. The ones in grey are coming. We have current projects and current papers. We just haven't published it yet. So there's Steve's shortest path stuff, max flow, linear programming, clustering, even stuff in software testing, anomaly detections, that's Savandi's work. So there's lots of stuff here, and graphs are really important. What we've discovered is that the features of a graph matter, not just to graph problems, but other problems as well. So very quickly, we have in our library, we have 18 features of graphs that we measure. There are 5 basic features of graphs, just node and edge statistics, the number of nodes, the number of edges, the density, the mean node degree, standard deviation of node degree, basic things. There's 8 features to do with cycles and paths on a graph, to do with the diameter and average path length, clustering coefficient, and measures of bipartivity of the graph. And there are 5 features that come from the adjacency and Laplacian matrices. And in particular, the energy of the graph turns out to be quite important for some problems. So the energy is the mean of the absolute values of the eigenvalues of the adjacency matrix, right? It's an important description of a network, as is the algebraic connectivity, which reflects how well connected a graph is. So just to give you a couple of examples of how this has turned out to be important. So this is our paper published in Computers and Operations Research in 2015 on graph coloring, where we discovered that when a graph has a very high energy, that was that one I just said before, the mean of the eigenvalues of the blah, blah, blah. When it has a very high energy, it turns out that that makes graph coloring very hard for most meta-heuristics, and that there's one algorithm that surprises us with how good it is, and the most powerful algorithm has a weakness for high energy graphs. So that was a nice little insight. And even for a problem that's not on a graph, like software testing, how do you test a piece of software? We can construct a graph We can construct, every computer program can be expressed as a control flow graph of procedures that lead to another procedure, etc. And from that graph, you can measure heaps and heaps of things about them. Some of these features are what I just talked about. And it turns out that these features are quite predictive of whether a particular software testing approach is going to be successful. So graph features are really important. My open challenges for all of you interested in networks, we probably need some more thought to go into the design of new graph features. I had 18 features there. There's so many more things we could be measuring about graphs, and given the importance I find of understanding a graph structure and its criticality for explaining the performance of algorithms working on graphs, any thoughts about new graph features that are not currently being covered would be very welcome. We need more work to go into the mathematical approximation of upper and lower bounds of those features. The density of a graph, we know the upper and lower bounds. We know it goes between 0 and 1. But there's many other features like the algebraic connectivity where there's history, you know, decades of work in graph theory to get tighter and tighter upper and lower bounds on how the algebraic connectivity of a graph is bounded by its density, for instance, but they're not tight enough. And the reason I care about upper and lower bounds of these features is because it gives me my red boundary. The red boundary of the instance space is mathematically defined using the upper and lower bounds of the features. And if they're not tight enough, I don't get a tight enough boundary. I don't get a tight enough sense of where all possible instances could lie. And finally, there's many opportunities for doing some interesting new work on constructing graphs from problems that are not on graphs, but have a graph underpinning if you care to interpret it that way. So I already talked about timetabling as an example, but you know, things like linear programming where you can have the variable constraint system being set up as a variable constraint graph, and then you can measure things about that. Control flow graphs for computer programs, cluster structure you could represent as a graph, and conflict graphs for constraint handling as well. So if we can construct graphs from problems, then it opens the door to measure a whole bunch of things from that. Just quickly, Matilda user accounts have been created from over 50 groups around the world since we launched in the middle of 2019. It's open source for academic use. We also have industry partners that are working with us on some research contracts, proof of concepts at the moment. So if you would like to use instance space analysis in Matilda, you just need to go to the website and click the getting started button, and you can create an account and start doing it. And I will stop there. Thank you.